Welcome back. We're going to cover the sensation and perception chapter today. Sensation and perception are critical aspects of psychological development that are related to your ability to sense the world around you and the manner in which those sensations are processed by your brain. The terms sensation and perception specifically refer to two particular aspects of this process. The term sensation refers to all of the basic underlying biological principles that are related to acquiring sensations from outside your body, like light and sound and smell and taste, converting them from their original source into a receptor which generates an action potential and then sends a signal into your brain, so that the sensation that may be received in your finger as touch is actually processed as a series of electrical signals inside your brain through a vast array of circuits. Perception is the more traditional psychological aspect, where you're referring to the entire operation of the brain impinging upon that one basic sensation and all of the basic learning and memory that comes along with it. So all the things that had happened. So if you had touched a teddy bear, for example, and you talked about the sensation of it, it would just be referring to the softness of the teddy bear. But the perceptual aspect would involve all of the memories of teddy bears, the events that the teddy bear was related to, your memories of your youth, and so forth. So when we take a look at the definitions for sensation and perception, we don't look at them as one single definition. Sensation and perception are absolutely separate processes. And so the definition for sensation, generally given as the process by which energy is detected and processed by your nervous system, and the definition for perception, the process by which sensation is affected by prior learning and memory. So notice that sensation is a more basic process than perception. And in fact, that perception would not exist if sensation was removed. The process of perception requires that sensations generate the activity related to prior learning and memory. Sensations themselves are just basically the underlying biological pathway that operates things. It's the difference between sensation being related to basic underlying biological principles that pass information around in your brain that are essentially the heart of how your brain operates and generates a psychological process. And perception is the more traditional psychological process which engages all of the various systems of your brain to generate one final output in a particular social context. Sensation and perception have traditionally been classified in two general ways, and these ways of a very general value in terms of this chapter. We'll really only talk about them here, but you should be aware of them because it gives you a little bit of context for understanding how this material is presented in this chapter. Bottom-up processing refers to times during which sensations are derived without any prior experience. So no prior learning, no prior memory. That there is a point where a sensation can occur when the sensation itself is brand new and is completely novel, and the individual has never experienced anything like that before. Of course, times like this would be extremely unique and most likely are associated with infants. For an infant that's born, on the day that they're born is going to be the first day they get exposed to air conditioning, exposed to artificial light, exposed to their mother's voice from outside of her body. They will see colors and shapes and other people They'll be wiped with rags to be cleaned off. They'll be swaddled. All of these things have never happened to a newborn child before. And so they have to be processed because the sensory receptors are all being affected, but there's no prior learning or memory associated with any of these events. So that would be referred to as bottom-up processing. There is virtually no bottom-up processing seen in an adult, although I have heard arguments be made for instances in which the astronauts back in the 1970s who had landed on the moon had experienced bottom-up processing because they had a great deal of difficulty determining the distances across the surface of the moon by just looking, giving that shading and all of the general perceptual cues that are typically on Earth that help you judge distance were somewhat messed up on the moon because of the moon's surface. Now, top-down processing is the much more likely scenario. Top-down processing refers to scenarios in which sensations derived and modified by prior experience. So the sensations you experience are largely modified by your prior experience. That is going to be the process that we will primarily work with because that is the process that you typically see with adults. One of the odd things you're going to see in this particular chapter is that your prior learning and memory will always override the actual sensory experience you're having at any one time. So that what you have already learned will be much more dominant in your thinking than what you're directly experiencing at any one moment. And that may actually seem rather backward and incorrect. If you designed a being to be as accurate as possible, wouldn't you want them to recognize what they're experiencing at that moment to be as accurate as possible? But I wasn't there when human beings were created, so this is the process that you're going to see take place, and it will become an issue for understanding how human beings make decisions about the world around them and what kinds of things they focus on that may drive their decisions incorrectly. So let's take a look at a question. Which do you suppose is the most basic factor in terms of sensation and perception? And the answer there is, of course, A, sensory reception. In terms of sensation and perception, if sensation is gone, then there cannot be any perception, because perception is the process of learning and memory that is pulled out of the brain from the experience of a sensation at any one moment. Without the sensation, you will not engage the prior learning and memory. And in fact, there would not be any prior learning and memory without a basic sensation. So sensory reception is always the most basic key to this whole process. Now, before we carry on with this chapter, there's kind of an old philosophical view about sensation and perception. As you might imagine, philosophers around the world for thousands of years have actually argued whether or not what you see in the world is what you actually get. Does food really taste the way it tastes? When you look at a tree, is that what's actually there, the tree, or is in some way your brain conjuring up a reality of a thing that's outside your body? And of course, from a philosophical standpoint, you can argue it one way or the other, but you don't really start to see any empirically derived answers to these philosophical questions until you get to the 1820s, as we'll see in short time. And from the 1820s until today, the evidence has largely pointed to the fact that what you see is not at all what you get. That is, all of the experiences that you have from your senses are actually very corrupted versions of the things that are outside your body. And so the concept of naive realism, the idea that what you see is what's actually there, what you hear is what's actually there, what you taste is actually there. That concept of naive realism is not used at all today. In fact, is essentially brought up, like I'm doing now, as a straw man to just knock down, because the concept of naive realism has a great deal of evidence against it, which we're going to see right in the very beginning of this chapter. So consider this question. Which of the following statements is true regarding how we understand the naive realism theory today? And the best answer there is C. The brain constructs a reality from its available inputs. That's the best answer anybody could give you in the 21st century. And in fact, this idea even extends back to the 1800s, when early research on sensation and perception was actually being done in some of the early psychological laboratories that were developed at the time. So let's understand how sensation and perception turned into the field that we understand it today. Back in the 1820s, which is, by the way, a time period I told you back in chapter 1 that we will talk about again and again. Back in the 1820s, there were a pair of brothers, Ernst Weber and his brother. Ernst Weber was a medical doctor and his brother was a physicist. In their spare time, they conducted scientific experiments on physics. Now consider the time period. If it's the 1820s, the field of physics has been around for about 220 years. That's a historical aspect from chapter 1. Physicists are feeling pretty good about themselves and their view of the world. They have lots of mathematical reasoning, lots of good models, lots of data that keep supporting the same ideas. But they don't have some things that we even take for granted today, and that is basic measures of many sensory aspects of the world. For example, if I asked you, how would you measure the amount of light that's in your room right now? Or how much volume is actually coming out of the speakers as you listen to me? Now, those kinds of questions, how much light is in the room, how much noise is in the room, can be answered very easily with modern electronic equipment. But consider, you're in the 1820s. There are no electronics. There's some very rudimentary control of electricity at the time, but there's not even a light bulb. Certainly no electronics. So under those circumstances, the field of physics does not have good measurements of brightness or color or even sound. And so what the Weber brothers are doing in their spare time is trying to generate scales for these aspects that are difficult to measure. Now, without electronic equipment, one of the ways in which the Weber brothers can do this work is by using human subjects to report how they experience something. And some of the earliest work that they did was based on touch. So they estimated how much a person could feel being touched with a metal rod, for example, or lifting a weight. There's a variety of other aspects that are related to touch, such as temperature, that they also try to estimate. Now, the only way that they could actually determine how a human experiences these things to try to create a scale was to stimulate the human, poke a person with a rod, and then ask them, on a scale of 1 to 10, how did it feel? Or, poke the person with a rod and then come back and then poke them a second time, much more forcefully, and then have them gauge the difference between the two. There has to be some way. And a human being is essentially a device that will actually give you an answer. Because, again, there's no electronic equipment or other types of scales of measurement in this case. For the various types of things that the Weber brothers were assessing, what they found is similar to the way I've drawn this figure on the screen. This figure represents two functions. The blue function, which is a straight line, represents the amount of energy of a particular stimulus. In this case, I've given it the hypothetical value of brightness, because brightness is an easy one to envision. Now, the red line refers to the perceptual experience of the person as they experience the brightness itself. And as you can see, if there is a direct measurement of light in a room, which is an objective measure, so that you take a dark room, you fill it with candles, and you light the candles to different degrees, and then you put them out and you light different numbers of them. So you could light 5 candles, 10 candles, 15 candles, and so forth, and have a person judge the amount of brightness in the room. The ratings that they give you regarding the brightness of the candles will be represented by the red function. And what this red function shows is that in terms of brightness, individuals will overestimate the lower ranges of brightness and then underestimate the higher ranges of brightness. And this was actually a really rather odd finding that was very consistent across all of the various sensory experiences that the Webers had assessed. In fact, some of them are curvilinear in the way that I've drawn here. Others are underestimates at low ranges and then much higher estimates for the higher ranges. And a handful eventually of some sensory experiences are going to track the blue function so that the person's ability to detect a stimulus is actually going to be very close to the amount of energy of that stimulus itself. Why all of this is very important is because the red function is actually a much more common representation of how people experience sensory experiences as opposed to the blue function. That is to say, regardless of the type of sensory experience you have, your body processes the experience of it differently than the amount of energy that's actually outside your body. Consequently, your description of what's outside your body is essentially incorrect most of the time. Even in this particular case with the figure on the screen right now, those two functions overlap only at two places. The first place they overlap is when both values are 0, and then the second place they overlap is where they cross over. Every other time, the person who represents the sensory experience they have is actually inaccurate from the reality that's outside their body. And that became a very important point in the early study of these sensory experiences. In fact, this process will later develop into what we'll call the field of psychophysics. As the Weber brothers did this work over time, one of the things that they found was that there was a consistent pattern amongst the perceptions of people that were related to the degree to which they experienced the perception. And you'll see that in what's called the Weber fraction. The Weber fraction is a mathematical relationship that is connected to the amount that you have to increase the energy outside a person's body before a person actually detects it. And you'll see that in two algebraically equivalent equations right here on the screen. The first equation is delta phi equals a constant times phi. Well, what does that mean? Phi is the Greek letter that represents the amount of energy that a person is experiencing. And the C is just a constant. So in this first version of the equation, a constant of some amount times the amount of energy that you're exposed to. So let's say brightness or amount of weight that you're lifting. A constant times that type of experience is going to tell you how much change is necessary to occur before you notice a difference. Okay? And that's the delta aspect. The delta phi aspect is telling you how much you must change the stimulus in its physical intensity outside the body before a person can actually detect it. So you could algebraically rearrange these terms, and you can divide delta phi by phi itself to automatically get the value of the constant. And since 1834, when this type of work was actually published, researchers who are primarily in biology at this time in history, and ultimately psychologists starting in 1879, will be using this basic process to understand the relationship between energy sources outside the body and the likelihood that a person notices a change. Now notice something about this equation. In the left-hand version of this equation, a constant is multiplied times some amount of energy that you're exposed to. So let's just say it's brightness. Some constant multiplied by the amount of brightness that you're being exposed to will tell you how much brighter it needs to be before a person notices that it's brighter in the room. That's telling you that there's a lack of sensitivity in the human nervous system, that the brightness can literally get more and more intense outside the person's body, but they won't notice it. Their eye doesn't detect it. Really, kind of in a much broader sense, their overall nervous system does not detect the increase in intensity. And so even though you are increasing the brightness outside of them in a laboratory experiment, the person tells you that they can't notice any increase in brightness. And this is true for all of your sensory experiences. It also tells you that with a constant being a constant, let's say it was 10%, that the amount of change that must occur over time actually has to get larger and larger. So if we did a shopping analogy here, 10% of a dollar is just a dime, but 10% of $100 is $10, and 10% of $1,000 is $100. It's always the same constant, but as you go to a higher and higher level of intensity on your scale, here being greater and greater numbers, the absolute difference that you must change before a person notices anything becomes larger and larger. And this will actually affect a vast array of things in the field of psychology. This point is establishing essentially how you, as a human being, notice that anything has actually changed in your environment. And it's going to apply to everything, not just basic sensory experiences like the sun went behind the clouds and you noticed that briefly it had become slightly darker where you were, but rather This process is going to apply to how well medical doctors can estimate from your symptoms that you're sick, or the likelihood that they will misdiagnose you with another disorder that has many overlapping symptoms. It will affect your ability to notice that another person is acting strangely or seems especially happy. If you're a clinician and you're working with a patient in therapy, at what point do you start to notice that therapy's paying off and that their behavior is changing? For you to perceive these things actually all falls under the same sort of venue for you recognizing change in the environment. So the kinds of things that we have been working with since the beginning of the semester have all been very basic processes that apply across the board universally in all situations. And this is very much one of those cases. You can never answer any question in psychology without also asking something about the likelihood that a person recognized that change had occurred. The Weber brothers did their work in the 1820s. They moved as slow as a snail walking through molasses before they published their work in 1834. Then, after about 20 years or so, Gustav Fechner, another research scientist also from Germany, started to pull on the work that the Webers had done. Fechner was trained as a physicist, so he had a substantial background in mathematics, but as a physicist, he was actually somewhat bored with traditional physics at that time, and he wanted to ask broader questions about life and how people experience things. He was thinking much, much more broadly regarding human activity rather than kind of the classical physics of the time. And that started to move him over into biology. Now remember, it's the 1850s, and it's a solid 2 decades before the field of psychology gets started. So there are no psychologists to talk to, and the people that are working on biology are really the closest thing you have to any aspect of understanding human behavior at that time. And what Fechner starts to do is he draws on the work of the Weber brothers, and he mathematizes the work of the Weber brothers. Because the Weber brothers, even though I've already showed you an equation for the Weber fraction, the Weber fraction was actually written out in text in the original writing in 1834. They had a strong sense of that aspect of a constant influencing the likelihood that you would recognize a difference. But Fechner, with his greater mathematical abilities, was able to pull that material together and actually create the equation that you've already seen. So the Weber fraction was discovered by the Webers, but it was never actually a written equation until Fechner applied his mathematical abilities to it in the 1850s and then named it the Weber fraction after the two brothers who had discovered it some 30 years before. Now, what Fechner's actually doing in this case is recognizing how there's a relationship between the external sources of energy outside your body and the manner in which you perceive them. And so he creates a new word. That word is psychophysics. Psychophysics became the field that Gustav Fechner made, and the field of psychophysics is still with us today in a much more complicated fashion than it was in its original form in the 1850s. What Gustav Fechner did was he attempted to make a scale of human sensory experience, and he wanted to lay that next to an actual scale of external energy to show how external energy sources and internal human perceptions were different from each other. And to do that, what he did is he made what's called the just noticeable difference scale. The just noticeable difference, which is frequently referred to as the JND, and I may just refer to it as JND in a simpler sense, but that's perfectly appropriate terminology in this case. Fechner made a scale of JNDs. Now try to imagine in the Weber equation, if a constant of 10% is applied to the amount of weight that you're lifting before you can notice a change, if I'm picking up a 10-pound weight, then everything between 9 pounds and 11 pounds feels the same because that's 1 pound down and 1 pound up, right? I'm picking up a 10-pound weight, 10% of that is 1 pound. So everything from about 9 pounds up to 11 pounds should feel the same because it's within the 1 pound range plus or minus the amount of weight I'm picking up. Now, of course, in reality, the 10% scale is being used in this case for simplicity, for simple numbers. The actual measurement scale for lifted weights is much smaller than 10%. But let's stick with 10% as a basic analogy to understand the scale. If we learn that a 10% difference in weight is necessary before a person notices that a weight becomes heavier, then that would mean lifting a 10-pound weight means we have to get up to 11 pounds to notice the difference. That means that if we're picking up a 50-pound weight, we have to get up to 55 pounds because 5 pounds is 10% of the 50. If we're picking up a 100-pound weight, then we have to get to 110 pounds because 10 pounds is 10% of the 100. If we could pick up a 200-pound weight, then it's going to be 220 pounds that will have to be on the barbell before we notice it's heavier. And if you could pick up 300 pounds in this scenario, you would have to get to about 330 pounds before you would notice that the weight had actually gotten heavier. It is, of course, getting heavier, but you can't feel it getting heavier in all these cases. Now, if you look at a scale like that, the scale of change is always going to be modified based on the amount of weight that you're lifting. So you could lift any amount of weight, and then the amount that would be increased from that amount, which is always 10%, is still always a constantly increasing raw score that has to be added to the weight that you originally started with. That is essentially the just noticeable difference scale. And that scale was formed for every sensory experience that Fechner could study back in the 1850s. So this became the very first psychological scale of measurement ever created. So Fechner's role in this whole story was to create the word psychophysics, establish a new field of study, mathematize the work of the Weber brothers, creating a specific equation that you just saw on the previous slide, and then to make the very first psychological scale of measurement, the just noticeable difference scale. And this whole field of study of psychophysics will essentially remain unchanged in the form that I've just given it to you for about the next 100 years before the next significant advance occurs to it in the early 1950s. And that's the process that we're going to go to now. After 100 years or so of work on psychophysics, a lot of scales of measurement are made. A lot of specific work is actually done on understanding whether it's humans or animals, the degree to which they could detect different types of stimuli. There are some basic assumptions that are made in the 1850s by Fechner that unfortunately turned out to be incorrect and had to be fixed in the 20th century. One of the assumptions that Fechner made was that if a nervous system is being stimulated, then it's operating. Right? Now, Fechner doesn't know anything about action potentials. He just knows there's electricity in the nervous system, and if you poke somebody or show them a light or ring a bell, they hear it, they see it, they feel it, and then that generates some activity in their nervous system. Now, the part of the assumption that he made that was incorrect was that when you're not being stimulated, that your nervous system just lies dormant. It's not doing anything. That assumption turns out to be incorrect. By the time you get to the 20th century and you have much better scientific equipment and much more study of the nervous system, you'll find that the nervous system is extremely busy. It's always active. And I've talked about this in general in chapter 2 by giving you the general statement. 100% of your nervous system is active 100% of the time. Right? And remember, that doesn't mean there's an action potential in every single cell all the time. That's not true, but nothing ever shuts down. Everything has the opportunity to function. And in fact, with the way the complexity of the circuitry of the brain has laid everything out, signals from receptors get sent into the brain and they continue to get distributed around the brain and affect different systems for lengthy periods of time. So that the brain is very, very active, not just from the inputs that come from the receptors directly, but even after that point, the distribution of action potentials within the brain itself as different systems are influencing each other based on the rules of action potentials and neurochemistry that we talked about back in chapter 2. Now, in the mid-20th century that all of that is recognized, one of the things that the more finely tuned equipment in the laboratories in the 20th century are starting to detect is that individuals believe that stimuli outside their body has occurred when actually it was an internal experience that had happened. So that is, by the 1950s, you can start to distinguish between whether or not a stimulus had occurred outside of a person and they detected it, or whether or not a stimulus had actually occurred as a result of the activity of an internal circuit and made the person think that it was actually something that occurred outside them. And with that strange type of occurrence, a new type of methodology had to be developed. And that's where we wind up here in the 1950s, looking at signal detection theory. Signal detection theory takes into account the fact that the internal operation of the nervous system may generate signals in pathways that will lead a person to perceive that an event had occurred outside of their body when actually it was an entirely internal experience and is just being misperceived. So when you take a look at this, signal detection theory is recognizing that all stimuli that occur within background noise. And background noise is the internal experience of your nervous system itself. Some of it you recognize as internal, other parts of it you may think are external, but you can't tell the difference between the two. So if you want to get very fine measurements of just how well a person can detect cues outside their body so that you can refine your understanding of psychophysics, you're going to have to move to this methodology. Like many things you're going to see throughout the semester, psychologists oftentimes solve the problem by dichotomizing particular events. Like in this case, either a stimulus occurs or it doesn't occur. It's either present or it's absent. And then, whether the stimulus had occurred or didn't occur, a person's going to experience it as having occurred, or they will not have noticed it. So if you ask a person, did the light turn on? They'll say, yes, it did, or they'll say, no, it didn't. When you take a look at the possibilities, if a light turns on and the person sees it, that is a correct detection. If a light is not on and the person says, no, the light was never on, then that is also a correct rejection. Those are two correct answers out of the four possibilities. The other two possibilities, however, are incorrect. So let's say a stimulus does occur, but the person misses it. So they don't notice it. You've turned on a light, then you turned it off, then you ask the person, did you see the light? And they say, no, there was no light. They missed it. So that's called a miss. And the other possibility is that the stimulus was never turned on, but possibly through misunderstanding an internal experience or some other possibility, a person thought that the light was turned on, and therefore you call that a false alarm. A scenario in which a person thought a thing had occurred even though it did not. Whenever you get a decision process set up in a 2x2 cell arrangement like this, you can use vast amounts of mathematics to improve your ability to understand in fine detail how your system operates. Now, we won't be going into that, but if you like biology, if you like aspects of psychology, and you want to go to graduate school and engage in a lot of mathematics, the field of psychophysics is for you, because in this arrangement, a lot of mathematical derivations actually occur. Now, let's take a look at a question. Which of the following represents background noise in the sensory system? And the correct answer there is E. All of the above are background noise. Consider A. Let's suppose we were in an experiment and we wanted to evaluate the least amount of sound that you could hear as a human being. So we're essentially testing the human auditory system for its absolute sensitivity. If we placed you in a secluded room that eliminated all outside noise, and you can actually find these things on YouTube to take a look at them, because they're usually connected with ridiculous stories that if you're placed in a room of absolute silence, you go mentally ill. That's the nonsense part of it. It's just a quiet room, and these rooms are actually engineered for good purposes, for engineers, for physicists, and psychologists can draw on them as well in scenarios like this. So suppose you're placed in one of these rooms. If you sat down in a chair in absolute silence, there would be noise that you could not get rid of, and that would be the sound of your own heartbeat. In a room so quiet, you would actually begin to hear your own heartbeat. In fact, because your heart is beating and blood is moving through your body, the blood moving in the capillaries near your cochlea will actually cause vibrations that will be detected by your auditory system, so you literally will hear the blood flowing through your head. Now, it's not possible to turn those things off, right? If you want to evaluate the least amount of noise that a person can hear, you're stuck with this background noise of a beating heart and blood flow, because if you turned off the person's beating heart and their blood flow, they're going to, of course, pass out and die, and you're not going to be able to get any measurements any longer. That's a big no-no for you. What if you did this with light? What if you put a person in an enclosed cubicle with no light in it, so it was absolutely dark? You gave them 20 minutes to dark adapt so that their eyes were settled and they were prepared to be tested. There are going to be some background sources of light in the room anyway. They're not actually in the room. It's not gamma radiation coming from outer space. It's random activity of your retina that's occurring as a result of the pressure in your eye and metabolic activity in your retina that is causing action potentials to occur in random cells in your retina. And once the retinal cell fires, it generates an action potential which travels back to your occipital lobe and gets detected as a tiny, brief moment of light. And because you're not looking at an object that has any shape or color, they just appear as tiny dots. So even you could do this now. If you just close your eyes, gently put your hands over your eyes themselves, you will see a whole series of tiny dots. Those tiny dots are simply random activity from the cells in your retina. Now, why is this background noise? Well, you're sitting in a dark room, and with modern equipment, I can present to you a light that is physically small and very dim, so that the light that randomly occurs that you experience from your retina is actually more powerful than the light that I'm showing you outside your body. And so that the background noise in your nervous system is overwhelming the actual sensory signal outside your body. As I either increase the size of the light, which will clearly distinguish it from the tiny dot flashes that you experience that come from your retina, or if I intensify the light flash in the experiment, then it will also then become distinguished from the random activity from your retina, and then you'll be able to detect it. So 2 simple ways to make sure that the signal that's outside your body is detected is to make it physically larger than the typical dots that you generally experience, or to increase its intensity. Tingling in your skin is always an aspect of touch that would modify what you experience. If I asked you to pick up a weight, even something as light as a pen or a pencil, if you pick it up and hold it in your palm out in front of you, you're not just picking up that pencil, you're also lifting your own skeletal system. And you're literally also lifting your own muscles. So when you consider how your ability to detect weight is determined by the overall amount of weight you're lifting, picking up that pencil, which seems like a very light object and should be very low on the just noticeable difference scale, should result in a very accurate measure of its weight. You have to realize now that you're not just lifting up a pencil, but you're lifting up your own arm. The bones in your arm, the blood in your arm, the muscle in your arm, and then you're adding a pencil to that. And now in that entire context, you're judging the weight of the pencil itself, which makes it feel much lighter than it actually is, because the pencil is only a small amount of the total amount of weight you're actually lifting, your arm being much, much heavier than a pencil. So let's take a look at a video that's going to reiterate everything I said in, I think, a much more entertaining fashion. This will be very straightforward, and it will follow the same story of Fechner's just noticeable difference scale and the work of Weber, all in terms of lifted weights.
Herbart reckoned that each new experience was added to the ones you'd already had, and that as each new experience changed your total experience, it changed you, but that you were only aware of the change if something happened to make you aware. Something that caused the event to cross your threshold of consciousness, a concept Herbart invented and proceeded to measure, thus turning psychology into the exact science it is today. Which is why I'm telling you this in the mysterious East. Because a guy who was at college with a friend of Herbart's brother was deeply into Eastern mysticism and went to seances and wrote about the souls of flowers and such like, and was called Fechner, took Herbart's ideas and turned them into what he called psychophysics, which was all about measuring awareness. If experiences, like this dance for instance, changed you like Herbart said, then at what stage in an experience did you notice it happening to you? At what stage did you become conscious of the effect on you? If you know what I mean. If you're still there. So it was Fechner and his college pal who came up with the next bright idea. An amazing new scientific law that I bet you've waited all your life to hear about. The law of the just noticeable difference. And I kid you not, this law would turn out to be of cosmic significance. Once, that is, around 1860, they'd got down to some really heavy research. This kind of heavy. The weightlifter is given more and more heavy weights to lift and asked if he notices. And I'm being perfectly serious. Turns out, whether you notice the difference with the extra weight depends on the weight you started with. And the scale of the difference is always the same. If you double the basic, you have to double the extra. So if for 100 kilograms it was 2, then for 200 kilograms, it's going to have to be 4. Okay, here's one for you. No muscles needed. 50 candles. Add 1. Notice the difference? You should. That's the just noticeable difference in light levels the human eye can detect between 50 and 51 candles.
In this measure, 50 to 51 candles, that should sound very much like a 19th century measure, and it is. Back in the 1800s, when there were no light bulbs and you did not have electronic equipment as we do today to make very fine differences in brightness, researchers had at their disposal only one source of light. That was a candle. And it worked well for them because a candle essentially produces the same size flame on it regardless of what candle you're using. As a result, you could add the number of candles you wanted in a room in a brightness experiment to see whether or not a person would notice the difference between 16 to 17 candles or 70 to 71 candles, and have them judge whether or not they noticed something was brighter, or even if you do it backwards by dousing some of the candles to see if they notice the difference from 65 candles down to 58 candles. So the estimate back in the 1800s was approximately 50 to 51 candles. And that estimate is actually essentially accurate still today, although we no longer measure things in terms of candles. Now, this leads us to a new question regarding how you notice these things occurring. And there are two basic processes that you would study in the field of psychophysics. One is called an absolute threshold, and the other is called a difference threshold. Now, these are very similar to each other in how they're done, so they're not going to be very difficult to understand. Let's take the more basic process that people generally think about. An absolute threshold is an estimate of the least amount of energy that you can experience. Okay, the least amount of energy you can experience. And that's the way a psychophysics experiment would always go. You're never looking for the most amount you can stand because you'd always burn somebody's eyes out with putting in too much light. You could crush them with weight. You could freeze them to death or boil them. The high end of a scale is completely irrelevant. The low end of the scale is going to be the side where you're trying to estimate what's the least amount that they could detect. That is, how sensitive is their detection system. Now, in a case like this, what you're going to do is take a stimulus well below the point at which you think the subject can detect it, and then slowly increase it. And as you increase the intensity of the stimulus, the probability that the person notices the stimulus rises until one point where you specifically want to see at what intensity is it that the person detects the cue 50% of the time. Now, why do you care about the amount that they detect it? Aren't you looking for when they always notice it? Well, actually, based on the 2x2 cell arrangement that we looked at a couple of slides ago, in signal detection theory, there are only 4 outcomes: a correct detection and a correct rejection, and then 2 incorrect answers, a miss and a false alarm. So with those 4 possibilities, if a person was in your experiment and they weren't paying attention and they didn't care about your data, and they just answered randomly yes and no, I noticed it, I didn't, they don't care, they would be correct 50% of the time by pure probability. So that establishes 50% as the lowest range at which you could justify in this methodology that a person can detect the cue. And so that is why 50% is actually used. So as you increase the intensity of the cue, you increase the probability that the subject detects it, and when that reaches 50% mark, that's what you use as your absolute threshold for detecting anything, whether it's light or sound or smells or taste or whatever it is that you're measuring. But it has to be one of your sensory systems. Now, the difference threshold operates the exact same way, except in a difference threshold, you're not going from a standpoint of trying to eliminate as much energy from the environment as possible, like placing a person in a dark room when you're going to evaluate how much light they're going to sound, or by placing them in a sound attenuation chamber when you're going to evaluate the amount of sound that they can hear. Instead, with a difference threshold, you specifically pick some amount of energy that will exist in the environment at that time, and then add to it or subtract from it to determine the likelihood that the person can notice a change. That is, what is the just noticeable difference under these conditions in which the energy source already exists. So if you're in the bright Florida sunshine in July at 1 o'clock in the afternoon and there's not a cloud in the sky, what's the likelihood that you'll notice one of those light flashes that are occurring naturally in your retina? Probably very little, right? Because there's so much external light that the light flashes that occur that you can see in a dark room with your eyes closed, your hands over your eyes, are going to be completely washed out by the bright Florida sunshine. And so you're going to need something much brighter to occur in your environment before you notice it flashing because there's so much light in the environment. And that's the story of a difference threshold, but that's of course the much more realistic scenario with just noticeable differences. Because when ever does realistically do you not have any stimulation to any of your receptor systems? There's always light going in your eye. Even realistically in a dark room, you probably have a radio alarm or some LED in your room that's there. And even if you didn't, you have those random light flashes from your retina. You can never turn off sound completely because your heart is always beating. You cannot turn off touch because there's always something impinging upon your skin, including temperature. You can never eliminate chemicals going up your nose and landing on your olfactory detectors. You can never eliminate any kind of taste from your tongue because saliva is there, bacteria is there, food may have been there, you brushed your teeth and now you taste mint. And of course, there's always gravity as well for your vestibular system, balance. You cannot eliminate any scenario in which there's going to be gravity, at least not realistically. And even if you took yourself and sent yourself into space where there's a point so far from everything that the detectable gravity was irrelevant, what you're going to notice is that you're floating. And so that's still, again, your vestibular system operating in that case, giving you a sensory experience. So difference thresholds are actually much more practical in a sense. And to evaluate the likelihood that you notice something from some particular energy level is the difference threshold story. Now let's take a look at this question. Which of the following reflects a difference threshold? And the correct answer, B. If your hair feels longer. You, on some day, will get your hair cut. You'll look in the mirror, you'll notice that it's shorter, it may even feel different, which it probably does. Now, your hair grows constantly, but it grows so slowly that you don't notice it changing day by day. After maybe 2 weeks, 3 weeks, 4 weeks, depending upon who you are, you might start to notice that it has gotten longer. You may feel it getting longer as a result of its weight, that is, it's tugging on your scalp or how your hair whisks around your head as you move. Or you might even notice from looking in a mirror in the morning as you get ready that your hair is actually a little bit longer. But there's going to be a point where you don't notice any change from the haircut, and then at some point later you will notice it. That point where you finally notice a change is a just noticeable difference. It may have come from a visual aspect, it may come from a tactile component, feeling of the hair on your head, but it came from one of your receptor systems, and under those circumstances, it established a just noticeable difference for that experience. Now, if you're going to do research on sensation, there are some basic rules that you have to follow. First, understand how a receptor works. For whichever sensory experience you're going to be evaluating, like light or sound or touch, you have to understand the physical limits of the receptor that will generate the very first action potential and the conditions under which it occurs. Would touch operate differently if you're in a warm environment versus a cold environment? So that is, would your ability to notice differences in lifted weights be affected by whether or not it's 30 degrees Fahrenheit or 105 degrees Fahrenheit? There's lots of questions you could ask there. And you have to understand the basic characteristics of the receptor, because the receptor is going to generate the action potential, which will get sent back to your brain, and then the analysis process can get started. So you have to know when those signals are coming in. You have to know what the brain pathways are, because as the brain pathways come in, they will branch out and affect other things. As we'll see throughout the semester, some of the light that goes in your eye winds up affecting hormonal activity and not vision. Sometimes sound that comes in your ear actually influences your vision. These types of crossover influences are natural in some circumstances, and in other cases, if they are too excessive, they're oftentimes referred to as synesthesia. So these scenarios have to be evaluated. You have to know which area of the brain processes a sensation to understand the circuitry in that area. And there is one basic rule about sensory research that you should be very aware of, and that is the weaker a stimulus, the less effect it will have on you. And the stronger a stimulus is, the greater the effect it will have on you. Now that is a very simple, straightforward rule. So why do I point out something so simple and straightforward? Well, it actually deals with a myth that's floating around behind this whole story. About 120 years ago, the idea of subliminal information was actually created. Now, the concept of subliminal information is that you can detect something that you don't notice and that it has an influence on you. That concept generally is not correct. The idea of subliminal information, especially the idea that you can manipulate people through subliminal information, is just incorrect. There's no good evidence for subliminal information. Now, to be clear, there is stimuli that will affect you, but if it's so weak, it can only affect you by small amounts. And that keeps with this basic rule. There are stimuli in the environment that you are not consciously aware of that will modify your behavior. But if those stimuli are so weak that you don't notice them, they can only have minor modifying influences on your behavior. The traditional story of subliminal information is that a very weak stimulus that you're not consciously aware of winds up having a grand effect, a very large effect. So you cue somebody in by saying, the cow jumps over the moon, and then they go into this hypnotic trance and they try to shoot the president. That's just ridiculous. That was a theoretical idea from the early 20th century that came out of clinical psychology, but there's no good evidence for it. This is a point where you have to be aware that the study of psychophysics actually does address a myth that still floats around about subliminal information. And this is something that you should just lay to rest. If anybody ever brings up subliminal information to you as a psychology student, you should know now to immediately say, no, there is no such thing as subliminal information.